Alright guys, so in this video we're going through the linear repeated roots. Alright, so last video we did the linear. So in this video we'll be going through the linear repeated. Alright, so that's a recap of the steps. Alright, so after you fully factorize the denominator, you analyze the types of roots that are present in the denominator, in which case we know the linear, and this video we're going to linear repeated. Alright, and then after you look at the type, you put it into its partial fraction form. Then you solve for the unknowns. Last video I did the elimination. So I'll do the equating coefficients in this video. And then after you solve your constants, you substitute it back, and that is it. Alright, so let's get into it. So you have the linear repeated. So I have the form ax plus b to the power n. So if you look at the denominator here, it is fully factorized. Alright, so it'll be 2x plus 4 to the power 2. And remember, as I told you, it just when you're writing it, the first one would be like the normal linear, and then you just increase by 1 each time you go in. And it will just stop at n, which in this case would be 2. So it'll be a, because it is a linear, so the numerator will be a constant. So it'll be a and 2x plus 4. In this case, the power 1, really have to write the 1. And then b plus b and 2x plus 4. And increase by 1 again, and it'll be 2. And the pattern will just continue, right? And then this one here, if you have after 3, so we start at 1, a, 3x plus 4 to the power 1, plus b, and 3x plus 4 to the power 2, and plus c, 3x plus 4 to the power 3. All right, you always stop at that. Yeah, and that is the linear repeated. All right, so have one more, this is the general form. All right, but that is the idea, the linear repeated. That's increasing from 1 up to the n, and that is linear, so the numerator will be a constant, right? Let's remember that. Right, so let's try this. So I've kind of started, but let's continue. So we have the first question here to express in partial fraction form. Look at the denominator, it is already fully factorized. So step 1 complete. Step 2, here right, it's in its partial fraction form. So there's a linear repeated. So that's like I showed you. So it'd be a and x plus 1 and increase plus b and x plus 1 squared. We have reached n, so we stop. Yeah. And step 2.5 of what? And by that multiply both sides by this denominator here on the left hand side. So when you multiply both sides by that, right? And this side will cancel. So you end up with this. On this side here now, you have your x plus 1. If you go into x plus 1, you will be left with x plus 1. Yeah, because this here, you can write it as x plus 1 and x plus 1. Yeah, if it confuses you. So x plus 1 into this, one of the x plus 1 will cancel and one will be left. All right, so then it b now, well, this and this could be. So that'd be plus b. Yeah, and at this point here now, we had to solve for the constant. So in this one, I'll show you the equating coefficients method, right? So in this part here, leave it as that, and here expand, so ax, and a plus a, and a plus b. So now I could group, so it'd be 3x. Remember, you're equating coefficients. So you had to group all the x's together, all the constants. So when you have ax here, and you have plus a plus b, which is our constant. Yeah? So now we could, let's say, equating coefficients of x. So we have, let's equate it to the 3x and ax. So 3x will equal to ax for 1, and then it has no constant. So therefore, anything that's not there is by default 0. And so 0 will equal to a plus b. Yeah, because a plus b is the constant. Yeah, and we can label that too. So from 1, we could actually solve for a. So 3x is equal to ax. X's will cancel, so a will equal to 3. Yeah, and then call this 3. And then you just substitute 3 into 2 to solve for b. So therefore, 3 plus b will equal to 0. So b will equal to minus 3. Yeah, and that is, you just solve for a and b. Yeah, so that is basically the equating coefficient. So yeah, when you equate it, when you get it down to this step here in orange, you just expand all the brackets and stuff. You group everything that have the same coefficient. So you group all the x's. If it had x squares, you group all the x squares and you group all the constants. And you're looking on both sides and you just equate an x with x squared, x squared, constants with constants. And then if you don't have anything, like if you have x squared on one side and you don't have anything on the other side, you just assume it to be zero. Well, it's not assume that it is zero. Because if something not there, obviously is zero. Right? After you do that, you have some small equations which you just have to solve simultaneously. Most of the time you'll be able to solve for one letter and then you just plug that letter back into the next equation to get the other letter and it'll just start a compound. You just need one. Yeah? So maybe you could mix the two methods together. So you could start using the elimination method to solve for one letter and then do the equating coefficient method. And now you have a letter to start with. Yeah. So it's not really one or the other. You could use both at the same time if you want to. Okay. But the equating coefficient method, it's more suited for more complex questions where you have to solve for like multiple letters and you have more complicated roots. Like if you had quadratic roots in the denominator, yeah, equating coefficients would be a nice method to use. Yeah, because when you have the one letter x or one x, might really get it to be zero, like in elimination. So it'd be better to expand and equate the coefficients and then solve for your constants. All right, so the last step, let's write it back into the form. So I'll just do it here. So 3x on x plus 1 squared. I think a was 3, so it'd be 3 on x plus 1, and it'll be minus 3 on x plus 1 squared. Um, that's it. All right, so that's it. You see it.